Okay, hi there, folks. In this video lesson, I am going to walk you through the derivation of 5 really important equations that we're going to be using this semester. And the equations are called the kinematics equations for motion with constant acceleration. And in fact, we've already met one of the equations. We've met the first one, which states that the velocity of an object can always be found as long as you know its initial velocity and the acceleration and the time that it spends accelerating. These equations that we're going to derive here all assume that the acceleration is nice and steady, it's constant, sometimes it's called uniform, and so that is the big assumption that I'm going to make when I show the derivation. So that's important to keep in mind. But they become very important, a really useful tool for solving word problems. And you'll see in my follow-up video that we can use this grid as a way of organizing the problems and solving them. So I'm going to get started here and show you where these equations are coming from. I think what I'll do first of all is simply to write down the first equation. And I'm not going to say too much about it. We've already met this equation. We know that this equation, it comes from the definition for acceleration. So you can recall that average acceleration is something that you can calculate all the time. Even if the acceleration is not constant, you can always calculate an average, and you would find the change in velocity and divide it by the time over which that happens. When we took this equation and rearrange it into this form, I know some people had questions about that. And the idea is it's really the same equation, right? Because delta V is Vf minus Vi over T. And you're just rearranging it. And so some people were asking, well, why is this special? And the reason it's special is because this equation that I'm writing on the left can be used to find the velocity, the final velocity at any time instant. Okay, so it assumes that the acceleration is constant. And so it would be okay for you to use any time you want and to calculate the final velocity. And you couldn't do that if the acceleration was not constant. So this equation, the way that it's written here, is really kind of special because you have to assume that the acceleration is constant in order to use it. Okay. All right, let's take a quick look at something we learned yesterday about displacement. Let's say that you have a graph of velocity versus time for an object which is having a constant acceleration. All right, we should know that if the object is having a constant acceleration, that graph is going to be linear. Okay, and we talked about the idea that the slope in this case is going to be rise over run. But if you look at this, your rise is actually your change in velocity, and your run is going to be a time. So when you find the slope of a line in a velocity time graph, you're really finding the change in velocity over time. And of course, that's just the acceleration. So this is something that we learned the other day, is that the slope of a graph of velocity versus time is equal to acceleration. Now, what else did we learn? We learned something about area. Okay? And if you say that you want to find the area underneath that particular line segment, you're really talking about finding the area under a right triangle. So that's equal to 1/2 base times height. So, and that makes sense. I mean, if you have constant acceleration, you should be getting a sloping line, and area would just be the area of a triangle. So the connection we made yesterday in the homework was that that area is actually the displacement. So the physics here is that area is equal to displacement. Okay, and if I'm going to show you that if you take base and height and you replace base and height with actual physics things from our graph, we'll have a new formula for finding displacement. So let's do that. So I'm going to take the 1/2 and bring it down. And now for my base, I'm going to look and I can see that the base of my triangle is actually time. So 1/2 times t. And my height, I guess you could say my height is delta v. Okay. But in this particular graph here, that delta v is caused because of acceleration. My change in velocity is equal to acceleration times time, right? Okay, coming back to our definition up here, that change in velocity must be equal to acceleration times time. So instead of writing delta v for my height, I'm going to actually just write acceleration times time. And let me simplify. So I have 1/2 times a times t squared. And this is the displacement, so I'll call it delta x. And that's actually a nice little formula for us, which will predict the amount of displacement that an object has if it's accelerating with constant acceleration. You can actually see the correspondence to the graphs we've been getting this week. We know that if you let a cart roll down a ramp, that its position time graph curves, right? So that curving graph agrees with my graph up above. There's basically both constant acceleration. Now that curve is a parabola, and it's actually coming from this relationship. So what you're really plotting here, if you're plotting time on the x-axis, you're plotting 1/2 at squared on the y-axis. So a math teacher would say that that's a parabola, because the vertical quantity is proportional to the horizontal quantity squared. So anyway, this formula is actually kind of nice. It tells us about the displacement of objects now if they're accelerating uniformly or constantly. Okay, and that is a parabola, definitely. Okay, now we're going to use that formula in a minute. That's going to be it's really helpful to know it, and we're gonna blend it into one of our big formulas. Before I do that, let me throw another formula in here. Let me show you a different way to find displacement. Again, coming back to the graph. And another way to find displacement would be to say that displacement is going to be equal to kind of average velocity times time. Okay. Now that even if the object is accelerating, that formula is still gonna hold true. Okay. And so now I'm going to be clever, and I'm going to say, well, average velocity. Let's see. If I'm average means my middle value. So if I'm starting here with some v initial, and I'm ending up here with some v final, my average is going to be kind of in the middle, right? It's like right on the middle there. So a math way to represent that would be to say, how do you find the average of those two endpoints? It's just going to be 1/2 times v initial plus v final. Right? If I said find the average of two numbers, you would add them together and divide by 2. So if I say find the average of two velocities, you add them and divide by 2. You multiply by the time interval, and you're going to find the displacement. Okay. So this is actually going to be our equation number 2. Right there. Okay. So equation number 1, I'll put a box around it. It's up here, and that's equation 2. This equation only works if acceleration is constant, because we're assuming that v initial and v final are connected by this line, and then you can always take an average. If this was not a linear graph, we could not use that formula. So again, you have to have a constant acceleration for that formula to work. Okay. All right. So that is that second equation. Now let's come back and see if we can blend this other guy into it. Get our third equation. So what I'm now going to do is I'm going to take equation number 2, I'm going to write it down again. Okay, so I'm just copying that down. And I am now going to do a substitution, and I'm going to substitute equation 1. All right, that means I'm going to get rid of v final, and I'm going to plug stuff in to get rid of v final altogether. Let's see what that looks like. So it's going to be 1/2 times v initial plus. Okay. I'm going to put big parentheses there and leave some space. Okay. So here it comes. So going back to equation 1. Equation 1 said v final is equal to v initial plus at. I am literally just going to copy that in here. Okay, and that's what I'm plugging in. There, make it really clear. Now, the reason I'm doing that is I want to come up with an equation that does not have v final in it, because maybe I don't know that in the problem. Maybe I don't care about it. So I'm getting rid of it, and that's the reason we're doing this. So let's simplify. That becomes 1/2 times 2 v initial plus at times t, and then I'll distribute. 1/2 times 2 is 1. There's a t in there, so I end up with v initial t plus 1/2 times a times t squared. Okay, so that t, it squares here. It doesn't square on the first term. Now, this is actually equation 4, and we didn't write 3 yet, but this is 4. And the beautiful thing about this equation is that it links together a lot of things, but it doesn't require that I know anything about the final velocity. So what's missing here in this equation is going to be final velocity. Okay, so I'll put VF with a line through it, because that's a good equation to use if I don't care about VF. Coming back up to equation 1, here, the thing that's missing, maybe you can tell, is going to be delta x. That's the thing I don't care about. Okay? And I think in equation 2, well, you could think about that for a second, but I hope you can see here that what you don't care about is acceleration. That doesn't mean there isn't acceleration, it just means that you don't need it to solve this problem. Okay? So we now have a set of equations here, which we have 3 of them so far, which can be usefully applied to these problems where you don't need that thing in there. I'm not going to work through the details of how you get to the next equation, but I'm going to write it. And this is actually equation number 3 on our list. And it looks a lot like equation 4, but there are 2 differences. Instead of v initial t, it's going to be v final t. And instead of plus 1/2 at squared, it's going to be minus 1/2 at squared. Okay? And so this formula actually is nice when you don't know about v initial and you don't care about it. Okay? How do you get that? You would get that equation basically by substituting here, and you would plug in v initial equals v final minus at. And then you would carry through a few steps. And I'm not going to do that here. I don't think you need to see that again. But you should know that what you end up with is a very similar type of equation. Okay. All right. So if you think about it so far, what different quantities that we have? We've got v final, v initial, we have acceleration, we have displacement. Okay, and we have time. Now, if you go back and you look at what we've crossed off so far, let's see, we have an equation that doesn't use this. We have an equation that doesn't use that. We have an equation that doesn't use displacement, and we have one that doesn't use acceleration. So we would really like to have one that doesn't use time. And the way that you get to that one is to basically hunt around for combining equations that involve time and substituting out. So we know that, for example, delta x is equal to 1/2 times v initial plus v final times t. But what I want to do is pick another equation that I can use to get rid of t. I want to knock that out. Okay, and if I substitute equation 1, that's going to work really nicely. Okay, so equation 1 is basically coming back again to this. And if you rearrange that, see if I can fit it in here, that would be saying, well, t is equal to v final minus v initial over acceleration. Okay. So this would be a good little algebra exercise for you, because if you take 1/2 times v initial plus v final times that, you're going to have to use the FOIL method. You're going to end up with 4 terms. There's a plus here, there's a minus here, so there's a little bit of algebra to be careful about. And I think you should do this. So I'm going to put a squiggle here, which means student does work. Little face. Okay. And if you do it right, you're going to get this equation, which is equation number 5. And this is a pretty well-known, famous equation that does not involve time at all. So this is your equation that doesn't have t in it. Okay. So I really encourage you to put in the mental effort of 2 or 3 lines of algebra to see if you can go from this to this. People, you're not going to be expected to derive these equations on a quiz or a test, don't worry, but I absolutely want you to understand where they're coming from and how you can use them. Okay? So I think what we've done here is we've come up with our 5 equations. Each equation is basically not addressing one of the variables, which sounds like a bad thing, but it's actually a good thing, because your physics problems usually only involve 4, not 5 of the variables. So to kind of end up here, if you look back at this sheet, you've got this list of equations, and I organized them in this way so that you can see that, like, equation 1 relates acceleration, initial velocity, final velocity, time, but it does nothing with displacement. So if you have a word problem that doesn't give you displacement and it doesn't ask you for it, equation 1, that's your guy. You want to go with that one. And likewise, as you go down the line, you can see that each one of these variables, of the 5 variables, kind of drops out of one of these equations, and that's going to be your guide for solving problems. So in the next shorter video, I promise, I'll show you an example of how to do one of these problems and use this grid, and then you guys can get going on it. Okay? Have fun.